Okay.
Yes.
Okay. 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 Hello, everyone. I am Agoston Sipos from the Budapest University of Technology and Economics, and I am going to present our research concerning multi-sided implicit surfacing. First, I briefly present the concept of multi-sided patches and some previous implicit methods developed for similar purposes. Then I introduce I-patches, a classic but unfortunately rarely cited implicit representation. Following that, I talk about our construction for building complex implicit surfaces from I-patches. Case studies and the summary will conclude the presentation. In geometric modeling, multi-sided patches occur in many cases. Most of the time, they are handled using standard representations, meaning that trim Trenzor product patches or sometimes discretized representations are used instead. However, the benefits of using exact multi-sided representations are indisputable. There are several papers about such parametric patches, but the use of implicit forms is less well developed. Implicit surfaces have several advantages, for example, with point classification, Boolean operations, and ray tracing. Implicit multi-sided patches also naturally connect to regular implicit surfaces, such as planes and cylinders and other surfaces. Implicit surfaces have an extensive literature dealing with various topics. Our current research is mainly related to blending methods, where two or more surfaces are smoothly connected by a multi-sided implicit patch. The first advances were published in the late 80s, but it is still a current topic due to the appearance of new graphics hardware and various applications in generative design. Interesting blending methods were introduced, for example, by Warren, Rockwood, and Guchmel et al. I would like to highlight two publications that are particularly important from one point of view. Bajaj and Im investigated fitting an implicit surface on curve and normal constraints, which could be used to fit a patch on an n-sided boundary loop, while Lee et al. And Hartmann developed functional splines, which are directly defined by boundary conditions. However, while these representations were important milestones, they are not easy to apply in the general case, and if there are shape irregularities, it is hard to find their reasons. Now let me introduce the basic properties of I-patches on which our work is based on. An I-patch is defined by pairs of primary and bounding surfaces, one pair for each side. Both are given in implicit form, and their intersection defines the boundary curves. The patch is created in such a way that it smoothly interpolates the primary surface at the boundary, thereby defining G1 or higher continuity constraints with adjacent surfaces. The top image shows the primary and bounding surfaces for a three-sided surface. The darker blue surfaces are the primaries, and they are intersected with the outer bounding surfaces to define the boundary curves. Then the surface is created as a smooth blend of the primaries. The resulting surface is shown here. The surface equation is directly composed from the evaluation of these primary and bounding surfaces, as can be seen in the formula. Free parameters are also included, but we will talk about them a bit later, what they mean. Here you can see the equation of a three-sided I-patch with G1 continuity and the reasoning why it works. On the ice boundary curve, the effect of all primaries with a different index vanishes as I equals 0. And the first term, and the term which includes pi also becomes 0 because we are on the pi primary as well. So the patch equation will be 0, which means that we are on the isosurface. It can be easily also proved that the gradient is also the same as the gradient of the primary surface times a constant multiplier. The interior of the I-patch is C infinity, and the I-patch guarantees case order geometric continuity to the primary surfaces. This follows from the fact that on the boundary pi and bi disappears, so they are zeros, and the case order continuity follows from the k+1 exponents in the equation. The I-patch degenerates if one of the surfaces used in its definition coincides with another, so this has to be avoided. While the pi-bi pair should never coincide with one another, if adjacent primaries or bonding surfaces are identical, the problem can be overcome by slightly modifying the equation. You can see the detailed discussion in the paper. We have discovered another equivalent form of the eye patch, which we call the rational form. It is a form similar to distance-based geometric definitions like an ellipse, where the formula is that it keeps a constant sum of distances from the focal points. This equation represents a simpler evaluation than the original equation, but it degenerates to 0/0 at the boundaries. Although we can use an alternative form for each boundary to evaluate the equation. This form is more useful from a theoretical viewpoint. For example, we proved in the paper that an eye patch defined by orthogonal elliptic cylinders, 3 orthogonal elliptic cylinders, and 3 planes as bounding surfaces will exactly reproduce an ellipsoid. Now we have seen how to create an eye patch when the primary and bounding surfaces are given, and this is as far as the original paper goes. In the following, we are going to investigate how these primaries and bounding surfaces can be constructed from simpler geometric entities and what sort of problems may arise. We will also look at some application-specific constructions later. Our input is a collection of corner points and tangent planes. We need to generate boundary curves that interpolate these points and the normal vectors, and at the same time possess a relatively simple implicit representation. This means that we have a hierarchy. If a configuration is if a configuration between 2 points is solvable by a straight line, we use a straight line. If it is solvable by a conic, we use a conic section. Otherwise, we use a more general implicit curve, the eye segment, which is the 2D analog of the eye patch itself. The primary surfaces, which we also call implicit ribbons, have to interpolate the boundary curve, the specified normal vectors, and it must have a consistent normal fence in between. We will see why in the next slide. The positive and the negative sides of the primary have to be consistent with the normal fence along the whole boundary. If 2 adjacent patches need to be smoothly connected, then they are supposed to share the same primary along the common boundary. If an implicit patch does not have normal vectors pointing in the same direction along the border, then internal singularities will occur where the normal flips. This means that the gradients of the primaries have to be oriented consistently by setting their positive half spaces in the correct direction. Then, the gradient of the eye patch is guaranteed to be scalar multiple of the gradient of the primaries, as we have already seen, and this direction only depends on the sign of the WI coefficients. Here I show you two-dimensional eye patches, which have to understand this problem. So here it's set consistently and it works. Here it's set inconsistently, and so it gives a totally bad result. The basic idea for creating a ribbon is generalizing Liming's method. If the boundary curve is a conic section, we can blend the tangential planes at the corner to a quadratic surface to acquire an appropriate ribbon. You can see it in the top right picture. When this is not possible, we use the eye patch equation itself to blend together the planes, using local perpendicular planes as bounding surfaces, and getting a ribbon that interpolates an eye segment boundary, as it can be seen in the bottom right picture. The bounding surface must also interpolate the boundary curve. It needs to be a surface which designates the location of the eye patch in the appropriate half space. You will see why in the next slide. I have already mentioned that the bounding surface should never coincide with the primary, because then they would not have the boundary curve as their intersection. But we have also experienced that if they are close to each other in the spanned angle, then various shape artifacts and numerical problems will arise, most likely. In the figure, this is avoided by fitting the bounding surface with the constraint that its gradient should interpolate the local binormal vector of the boundary curve. In this slide, I show examples to illustrate that the bad choice of ribbon and bonding surfaces can have a disastrous effect on the patch. If the bonding surface intersects the boundary loop, it certainly leads to shape errors, so another surface constructed in a different way, seen here, has to be used. A primary surface which abruptly changes its sign inside the patch might also lead to problems. Slightly modifying the ribbon's free parameters generally leads to acceptable solutions as shown in this picture. We have seen that there are some free parameters in the iPatch equation. They can be used for adjusting the interior of the patch. In these two images, we can see iPatches with the same boundary conditions interpolating different specified points in the middle, thus producing different shapes. It has to be noted that the scalar weights must not change sign, as we have already seen that it would flip the normal vectors. You can also see this example here to remember. We propose a method of setting the default coefficients. Assume that we have picked a good reference point in the middle of the patch, and we set the weighted algebraic distance, which was seen in the rational form of the iPatch, for all boundaries to a fixed number, so it equals all the other ones. This algorithm highly depends on the quality of the distance field and the reference point, but it usually works well. If it is not sufficiently good, the resulting coefficients can be used as an initial configuration for a refining algorithm that tunes or adjusts the coefficients. Now let us see two interesting applications where iPatches can be utilized. First application is polyhedral design. Here the patch corners are defined by the midpoints and the normals of the faces of the polyhedron. The generated curves define a dual network from which the ribbons and bonding surfaces are automatically generated. Then the loops are filled with iPatches. All surfaces are automatically connected with G1 continuity. Editing the control polyhedron is easy, and the shape of the implicit surface generally deforms in a natural way. Our other application is setback vertex blending. This means that the vertex of the polyhedron, denoted here by O, needs to be smoothly blended with the vertex blend joining to blended edges and the faces. These blends provide smooth connections to the edge blends and the faces, and so they often have a large number of sides. Our construction naturally handles this. See, for example, these 8 or 10-sided patches. And here you can see a composite vertex blend structure created from a polyhedron. So here are the faces that are not shown on the picture, and these are the blended vertices. So let me summarize our research. We have shown how to create a consistent control structure for iPatches, including the creation of primary and bonding surfaces. We have discussed how to adjust their interior, while we have pointed out that the creation of implicit patches may produce shape artifacts. We have also presented methods to detect and fix improper configurations. We have shown several examples for applying iPatches in polyhedral design and vertex blending. Thank you for your attention, and I will gladly try to answer your questions.
Thank you very much, Agustin. Are there any questions for the authors and speakers? Please don't hesitate to ask questions into the chat, either on Discord or in Zoom.
I have one small question about continuity. But it said it's in the article, but can you say one word about the G continuity on this iPatch, please?
So you mean
what can we obtain?
The case order geometric continuity?
Yes, what can we obtain on the borders?
So the construction guarantees that if we have the same primary and bounding surface at a given curve, along a given curve, then the iPatches that are constructed on the two sides based on these surfaces will connect with case order general continuity, where K is the exponent which is here in the equation. Of course, it is not necessarily a good idea to introduce a very large k, because then the degree of the equation will be very high. So most of the time we use the G1 continuity where the exponent was 2.
Okay.
Did I answer that?
Somehow.
Thank you, Agustin. So message to everyone. So don't hesitate to ask also question in text or to turn on your microphone to speak up. In the meantime, I will ask a question, as I do not see a question in the chat yet. So my question is about, you mentioned this notion of fullness.
Mm-hmm.
That conveys some intuition, but could you say a little bit more about it?
You mean like the difference between these? So, so what we informally call the fullness coefficient is this last coefficient, which is so this member of the equation is not affecting the boundary of the patch, only the inside, because on the boundaries it vanishes, and so that means that the interior can be modified using this one single coefficient without modifying the boundaries. It is a problem that this coefficient does not have a geometrical meaning. So what we most of the time what we did was to introduce just a point, and after we set these weight coefficients, then we can interpolate any given point by just solving this equation for W, and that's all. So that's what we informally called fullness, but sadly the coefficient does not have geometric meaning.
I understand, but do you think there is also a means to extend this approach so that you could provide automatic estimate of these parameters such that you I don't know, optimize an objective function? That
yes, we did some things like that, but I didn't want to go into that because of time problems. So what we did is that we use these heuristics first to acquire an initial parameter setting, and then we triangulated the patch and used an optimization based on some curvature based function, target function.
Thank you. So I see in the chat there is a question by Gerben Hettinger. The paper mentioned a triangulation method. Are the shown results ray traced or made using your triangulation method?
Well, yes, most of the time they are just triangulated. There is some picture that this picture is ray traced, for example, but so efficient ray tracing was not in the focus of the research yet. So hopefully it will be in the future. But other images are just triangulated.
By the way, that also suggests another question from me, as I don't see another question in the chat, so I will continue. So that's also a topic of like one of my favorite topic is how can we efficiently query such implicit surface with intersections queries, like with a line segment, with array, and so on. So how efficiently can you answer this type of query, and how reliable can this be?
What we did is that we took advantage of the fact that we know all the corner points, and as we know all the corner points, we can just fit a very simple parametric patch on the corner points, and then triangulate the parametric patch, which is a relatively easy task, and then project each of the parametric surfaces points on the implicit patch. And And of course, if it did not work for some reason because the parametric and the implicit patch were too distant from each other, then we modify the parametric patch.
Is it possible to rely upon, this idea of pencil of matrices in which you parameterize directly your the ray by a set of matrices and like to plug in this approach, this pencil of matrix approach by Laurent Buzet from INRIA?
I did not understand the notion, so.
Okay, no, it was a bit of a technical question. Sorry, so I was just asking whether.
So the point of the question is if it's if it is done efficiently.
No, I mean when you do like when you do intersect typically a parametric surface or even an implicit surface, so you have several ways to compute that, right? And one can be sometimes achieved using so-called pencil of matrices. So where you look at the rank defects and so on. So I was just asking whether this can be leveraged here in this context, but
maybe we did not
okay.
did not think about that.
So I do not see other questions into the chat. So thank you very much, Agustin, and to the authors of this paper. Thank you so much.
Thank you.
We have just 2 minutes for the switch. And I propose that we switch to the next speakers. So the next paper is entitled Data-Driven Quasi-Interpolant Spline Surfaces for Point Cloud Approximation. The authors are Andrea Raffo, who, as far as I could see, has 3 affiliations. So CINTEAF, University of Oslo, and also IMATI in Genova, Italy. And the other author is Silvia Biasotti from IMATI in Genoa, Italy. And the speaker should be Andrea Raffo.
Yes, can you see the screen?
Yes, we can see the screen. Don't hesitate to also turn on your camera. If you have one.
Okay, yeah. It's 3 months that I don't go to the hairdresser, so I guess I'm not really.
No problem. Okay. Yes, we can see the screen. That works. Please, Andrea.
Okay, so thanks for the introduction and for being here today. I'm going to present a novel quasi-interpolant spline approximation, which has been specifically designed to deal with perturbed data. First of all, why and what is quasi-interpolation? There are different definitions in the literature. We consider here methods that are defined as linear combination of B-splines. In the left picture, you can see an example of univariate B-spline in red. The coefficients of this linear combination are explicitly computed by some value, which are sampled from the function itself that we want to approximate. Quasi-interpolation schemes are popular because of their simplicity and efficiency, because they do not require to solve any linear system. They define infinite approximation schemes, and moreover, they can be potentially local and global methods, according to the data that we are studying. On the other hand, a big disadvantage is that most of traditional quasi-interpolant methods assume that the data are sampled from a mathematical function, which should satisfy some, let's say, some basic assumptions. Regularity assumption, for example, the function itself that we want to approximate should be at least C0, more often even C1. Here we want to define a more versatile tool because we would like also to be able to deal with perturbed data. So our approximation is again going to be expressed as a linear combination of B-splines. In this work, we are going to consider bivariate tensor product B-splines. And in this case, the coefficient of each B-spline is going to be expressed as a weighted average of an input point cloud. In order to have let's say, much clearer picture of what's going on, I suggest to focus your attention on the picture on the right. So we have an input point cloud in light blue, which has been obtained by sampling the red function and by adding some Gaussian noise. Then we consider the B-spline functions, the one in blue. And for each B-spline, we compute the control point by means of this weighted average. Then by considering the linear combination of the B-splines with the respective control point, we can obtain the approximation in orange. Just a few examples of weight function. We have what I guess most of you know, the k nearest neighbor function. Then we have characteristic or indicator weight function, and finally the Gaussian weight function. As an example, in the picture, we can see the estimation of control point in green, which has been computed by considering a weighted averages of the 10 closest points to the axis x equal to 1. Now, here k is set to be equal to 0 to 10, but of course, this is usually a free parameter to be fixed. So we must also decide how we are going to fix these free parameters in weight functions. Classical properties of cause interpolation are preserved. We have global and local methods, global and local bounds, sorry. The monotonicity and convexity of the, let's say, average trend of the point cloud is preserved. And we have all the properties that comes from the use of B-splines. So for example, we have local support, which means high parallelizability of our approach. As new aspects, we have an increased robustness to data perturbation, also thanks to the use of weight function that can be, let's say, chosen according to the input point cloud. And not in this paper, but in general, we have achieved also, let's say, an explicit formulation of the bias variance trade-off, according to the weight function that we are going to consider for a point cloud approximation. The paper focuses, as I said, on the bivariate setting, so bivariate tensor product B-splines. We have two situations that can describe our data-driven implementation. Basically, in case we are in a situation in which we have, let's say, a rich point cloud, then we take our input point cloud and we consider a partitioning into three subsets: training, validation, and test sets. The training set is used as input of the weighted averages. For example, I was talking just a few minutes ago about the 10 nearest neighbor. Well, the training point cloud is going to be an input of the 10 and n. Then the validation set is going to be used to fix three parameters, for example, the k in the k and n, or also the number of iteration of our algorithm. While the last point cloud, the test point cloud, is going to be used to compute a sort of generalization error, which is computed in a way that it's independent from the other two point clouds, the training and the validation point cloud. What is important here is that the training, validation, and test set should have the same somehow distribution and the same kind of perturbation of the initial dataset. So we should be able to preserve these properties. But there are some routines, for example, in MATLAB that can allow us to do this almost immediately. In case of insufficient data for this splitting, we consider as an alternative the k-fold cross validation. I don't have time to go into details, so feel free to ask questions or to, let's say, have a look at the paper for this case. But how does the data-driven implementation work in practice? As I said, we have an input point cloud. let's assume that we are in the data-rich situation. So we perform first a data preprocessing, which means that we are going to split our point cloud in training, validation, and test set. Then the training set is used as input of the weighted average, while the validation set is used in the parameter setting in order to fix free parameters, such as, for example, the K in the KNN. Now, if the approximation that we achieve is accurate enough, meaning that it satisfies an accuracy test, then we return this approximation together with the generalization error computed on the test set. For example, the mean square error computed on the test set. Otherwise, we globally refine the mesh where the validation error is showing that let's say the approximation is not good enough. And in general, we repeat step 2 and step 3 until the accuracy test is not satisfied. We have performed an initial comparative analysis by considering 3 real-world applications: surface reconstructions, terrain approximation, and data measurements. We consider point clouds of different size because we are interested in checking how the method works. We want to check both the situation in which we have plenty of data, but also real condition of sparsity. And in this case, keep in mind that a tensor product mesh, which contains only one element, is basically polynomial approximation. So it's still a case of interest. For our comparative analysis, we are going to consider, let's say, method which has proved to be highly resistant on real-world data, namely radial basis function with different kernels, Kriging, and multi-level B-spline approximation. For, let's say, assessing the quality of the approximation, we are going to consider statistics of absolute punctual error, for example, mean, standard deviation, and mean square error, the Hausdorff distance, or the L infinity norm when it makes sense. We start with an example of surface reconstruction. The picture on the top left represents our approximation when we consider a Gaussian weight function. The remaining pictures represent the absolute punctual error when we apply a threshold of 10 to the minus 3. So all the transparent points are below the threshold, while the remaining are above the threshold. This is just, let's say, quality representation, but in any case, it gives us, let's say, an insight of where we need to refine or where the error is bigger. For a quantitative comparison, we can have a look at the table. We can see that our method has similar results to the others when we consider the Hausdorff distance and the standard deviation, while it's slightly worse with respect to the mean and mean square error and mean square error. The box plot is just a part of a wider test in which we have, let's say, checked that the results of this approximation do not depend on the chosen partition of the initial point cloud into training, validation, and test set. Then we have 2 examples of terrain approximation. In the left column, we can see our approximation, while in the remaining, we have the absolute punctual error for our approximation and for the MBA. We consider here only our method and MBA because the point clouds span from 400,000 to 900,000 points, and the implementation which we have been using for the test do not scale to this to the size of these point clouds. Also, in this case, we can see that our approach is slightly better when it comes to the Hausdorff distance, while it's slightly worse when it comes to the remaining measures. And finally, we have example of data measurements. In the top left picture, you can see the initial dataset, which is in this case highly perturbed. It is a dataset from rainfall fields in Liguria, Italy. The remaining picture represents the absolute punctual error in this case, the threshold is set to 15. A quantitative analysis is shown in the table, and we can see that our method outperforms the other with respect to mean, standard deviation, and mean square error, while the results, if we consider the L infinity norm, are slightly worse. If you check the other simulation in the paper, you can see that, let's say, we have considered other 5 datasets for data measurements regarding rainfall fields, but nevertheless, there is not a clear winner when it comes to the L infinity norm. While if we consider the other measures, we are outperforming let's say, the classical approaches. As conclusions, we have applied a quasi-interpolation technique to perturb data by introducing a multi-level and data-driven algorithm. The performance of our method are aligned with other popular methods when it comes to, let's say, clean or mostly clean data, while our method outperforms the other when it comes to strongly perturbed data. As future work, we intend to pass from local to global representations, for example, by stitching together the local approximation that we have achieved so far, or by directly computing a trivariate implicit representation. We would like to pass from global to local refinement, for example, by considering LRB splines. And once these 2 points has been addressed, we would like also to extend the comparative analysis, for example, by considering new data, application, and methods. And that's all.
Thank you, Andrea. Thank you very much, Andrea.
Thank you.
Feel free to ask questions in the chat or in Discord. I'm currently watching the two, and I do not see yet a question in the chat, so I will have one. My first question is, you mentioned this progressive refinement, where you refine until you satisfy a certain accuracy.
Yes.
But sometimes they are also multi-objective. Sometimes you would like to have, typically you may want to have a trade-off, like a trade-off between complexity and accuracy, right? Like what's the complexity of your model versus accuracy? That's a balance, right, between 2 criteria.
Yes.
You have multi-objectives and things like that. So do you think your method can be extended?
Honestly, I don't know. We have performed some, let's say, both some numerical but also some theoretical studies about the computational complexity of the method. So there are some results. So far, we are using, let's say, a maximum number of iterations in order to stop the method if there is too much to refine. But we haven't got any results in, let's say, in as you suggested.
Mm-hmm. Yeah, the question when it's like that is that you may also have several optima, not just one. You may have like levels of details if you want, which are equally good.
Yeah.
So, and another question too is that in your method, you can also imagine that for improving the fitting with respect to the data, you can imagine that perhaps your method can be made more, I don't know, locally anisotropic with a sort of a tensor field and so on, right? Such that you again improve that balance, complexity, distortion, and so on, or just improve the fidelity or accuracy. So can this also be extended in that direction?
Probably yes.
Right, imagine you have ridges, right? Imagine you have a lot of
Let's
ridges.
say that now, up to now, we have controlled the computational complexity by, first of all, the complexity is different if you consider global or local supported weight functions. Up to now, we have, let's say, reduced the computational complexity by considering approximation of the weight functions. So even for example, when I'm considering a Gaussian weight function, which has a global support, instead of considering the function itself, which is going to zero quite rapidly, we are going to consider an approximation, for example, by combining it with indicator function or KNN. But this is the kind of, let's say, treat that we have been using for reducing the computational complexity.
I have a look in the chat, no more questions, but I will ask for another one in the meantime. Feel free to ask questions. Again, I repeat that. I see we have 22 participants now. That's great. So in your method, suppose we have outliers plus elsewhere variable noise, a noise that varies, right? So the same, is it possible to extend your method such that you can specify like a certain degree of resilience to outliers and also robustness to
potentially, yes, it's something we would like to do, because one second, up to now we have just performed some tests, but yes, it's something we are considering. For example, at least right now we were using the mean square error for the loss function, but we have found that there are, let's say, other measures that are more resistant to outlier, and so they can provide a better, let's say, evaluation of the final result.
Okay. No. There is a question in the chat by Mr. Ramanathan. Feel free to take the microphone also, but otherwise I will just report it orally. So you mentioned about splitting the data into train, validate, and test. What is the size of the data set and what is the ratio for splitting?
This is a difficult question. I mean, I checked, well, I didn't have the answer when I was taking the statistical course I had in Oslo, and I didn't find an answer online. So let's say just, it's somehow empirical. You should run some tests and see if basically if the validation error is dependent on or not on the final choice. If the variation is let's say quite important, then you should use k-fold cross validation. But usually, like, I mean, it's difficult to answer because it also depends on how the data is distributed. If it's uniform, if you have missing data, if you have outliers, like, you should also be able to make the split such that all the three subsets have somehow the same noise, the same outliers in the same places. So first of all, I guess that at least for a general data set, you should perform some tests.
And also, I have, in fact, a question relating to the loss. So do you think it could be the case that what you want to model is a surface, but a surface whose shape is correspond to a certain accuracy from the physical point of view? So it could be the case that after all, the loss function relate to something abstract that is connected to a specific physical simulation. So do you think your approach can be sort of generalized so as to query sort of an abstract interface to a physical simulation? Something like, you know, physics informed.
Maybe.
You know, some people start doing that in deep learning, you know, physics informed.
Okay.
Right? The loss function relates to the physics of a phenomenon.
Yeah, maybe, I don't know, honestly.
Okay, okay. So, message to everyone, feel free to ask for one last question. Otherwise, I will maybe ask for a last one so that we restarting at 4:20. Maybe my last question is regarding the regularity of the surface that you can generate. So again, there are many ways to characterize the regularity of a surface, but do you think this method is also amenable to enforce or to favor some notion of global regularity, including maybe like non-local symmetries or orbits or things like that? You know.
Yes, I mean, since it's expressed as a linear combination of B-splines, it shouldn't be too difficult to put some constraints, I guess.
Mm-hmm.
Yeah, for example, right now we are using regular mesh. With regular mesh, I mean that there is the maximum multiplicity at the boundary, and then yeah, whatever can happen in the let's say in the interior. But by using maximum multiplicity at the boundary, basically you are putting some interpolatory conditions. So you are somehow already enforcing some constraints, at least on the boundary.
Okay, there is okay, another question. In terms of properties, have you analyzed your method's performances in terms of curvature or some geometric properties?
Could you repeat the question? Sorry.
So in terms of properties, have you analyzed your method's performance in terms of curvature or some geometric properties?
Well, right now we have just considered this accuracy measure for the evaluations. There are some theoretical results that guarantee that basically they guarantee that our approximation will be in a certain region, so it's locally and globally bounded. And then we have some results regarding the shape of this final approximation, but we haven't considered the geometric properties for an evaluation, at least in this work.
Mm-hmm.
We have performed anyway. I mean, there is another work on arXiv in which we have performed some tests. In that case, it was the univariate case, but with application on imaging science and 3D models. In that case, the shape was very important. So I would say, yeah, there were more tests regarding the geometry at least.
Okay. Thank you very much, Andrea, and also thank you to Silvia. Thank you very much. That concludes this talk. Remember, you can also, for everyone, you can continue the discussion offline on Discord about each of these papers. So, Andrea, I invite you to maybe to mute your camera. And now the last talk is entitled on Hamiltonian cycles in the FCC grid. So the authors are Lydia Komi from the Faculty of Technical Sciences, University of Novi Sad in Serbia, and Paola Magillo from the Debris Lab, University of Genova in Italy.
Thank you for the presentation. Good afternoon, everybody. I'll try to show my screen. Okay. Do you see it?
Yes, perfect, Paola. Thank you.
But okay. Okay. The title is on Hamiltonian cycles in the FCC grid. And the first question is, what is the FCC grid? We are talking about how to tessellate 3D space. And we know that the only regular polyhedron which can tessellate the 3D space is the cube. But if we move from regular to general convex polyhedra, we have many other ways to tessellate the 3D space. And they are found, well, not only in the mind of mathematicians, but also in nature, in crystallography, for example, or also in new sciences like bioengineering. These two pictures, I've just found them on the internet by typing polyhedra tessellation 3D space, and they are used. This one is the FCC grid, but I will present it in more details. Okay, some examples of non-traditional grids. The diamond grid. One may think that the tetrahedron tessellates the space, but it is not true. In order to tessellate the space, we need this special truncated tetrahedron, which can fill the space if used not in just one orientation, but in two different orientations. And then there are also grids that are derive from the cubic grid. For example, the body-centered cubic grid has the basic voxel is this truncated octahedron, and it is so-called body-centered cubic grid because it can be, we can obtain it from the cubic grid by placing one seed at each vertex of the unit of the cubic grid and one seed in the center of each cube, and then taking the Voronoi diagram. This is the cell of the seed in the center of the cube. These are the seeds on the vertices and so on. And we can fill the space in this way. And now the grid that we consider here, face-centered cubic grid, the basic voxel is this strange shape, the rhombic dodecahedron. And again, this is obtained from a cubic grid by considering one seed in each vertex of the cube and one seed in the center of each face. That's why face-centered, in fact, the name is. Or equivalently, if we shift the cube half the edge length, we can put one seed in the center of the cube and one seed in the midpoint of each edge. And then we have the Voronoi cell of the center is this, the Voronoi cells of the centers of the vertical edges, and so on, and we fill the space. Now, when we have a grid, we have our 3D space is now discrete, and we can define a digital object as a finite connected set of voxels. And each object has a dual graph where the nodes are the voxels of the object, and two nodes have an arc between them if they share a face, if the voxels have a common face. A tree-like object is an object where the dual graph is a tree, like this one. And finally, we arrive at the questions we ask in this paper. The questions are about the existence of Hamiltonian cycles on the surface of voxels and objects in the FCC grid. We have to introduce another graph, which is the dual graph of the surface, the boundary surface of an object. Here the nodes are the faces and the arcs are, an arc exists between two faces if they share an edge. And our question is if Hamiltonian cycles exist on the boundary of a single voxel of an object in the FCC grid or generally in a grid, where a Hamiltonian cycle in a graph is a cycle which visits each node exactly once. In general, the problem of deciding if a cycle has an Hamiltonian cycle is NP complete, but we will consider special cases of graphs. We have already some results. On a single voxel, we wanted to characterize the Hamiltonian cycle's existence on the boundary of the voxel. And when I say the Hamiltonian cycles, I consider that two rotated versions of the cycle are the same. So the cycles are considered the modular rotation and symmetry. And from previous works, we have shown that the BCC voxel, this one has one Hamiltonian cycle, and the diamond voxel has one Hamiltonian cycle. And in this paper, we show that in the FCC voxel, there are 5 non-equivalent up to rotation and symmetry Hamiltonian cycles. And for a tree-like object, in the BCC grid and the diamond grid, we have shown that there is a Hamiltonian cycle on the boundary of each tree-like object. In the diamond grid, the object must be made of voxels with the same orientation. And in this paper, we also show that there is always a Hamiltonian cycle in the boundary of any tree-like object in the FCC grid. Now, I present the FCC voxels, some properties. The rhombic dodecahedron has 6 vertices that are located in the centers of the faces of the cube inscribing the voxel. It has and these are these six ones are called open vertices. Then there are another 8 vertices called closed vertices, which are located on the midpoint of the segment connecting the center and one vertex of the cube. And there are 12 rhombic faces that correspond to the edges of the cube. And okay, each rhombic face has 2 open vertices and 2 closed vertices. The open vertices have sharp angles and the others have obtuse angles, and each in one voxel, each closed vertex has 4 incident rhombic faces, and each closed vertex has 3 rhombic faces. Okay. Now, there are 2 propositions in the paper. Proposition 1 says that there are 5 Hamiltonian cycles connecting the faces of the FCC voxel. And in particular, there are 2 cycles that traverse, for some open vertex, they traverse all the 4 incident faces consecutively in this way. There is 1 Hamiltonian cycle connecting the 3 faces consecutively and the other one in another moment. And there are other 2 Hamiltonian cycles that don't traverse consecutively more than 2 faces for each open vertex. Now, the proof is by enumeration. It is a bit boring and easy. And here I will skip it, and I want just to show how these 5 cycles look like. And if I can, I will show them in okay, new share maybe in the 3D viewer, if I can. Okay. Okay. Do you see the voxel? I hope so. Okay, this is
Yes.
the basic voxel. Okay. And there are 5 cycles that I call C1, 2, 3, 4 to 5. The first, there are 2 that traverse some. For some vertex, they traverse all the 4 faces consecutively. One is this, and you see that here there must be a point. Okay, for this vertex marked with the point, the 4 faces are traversed consecutively, and it is the only one. In the opposite vertex, we have 2 and 1, 1. Then for other 2 vertices, we have 2 and 2. The other, and if I find the second one, okay, this is the same. And for the last one, and here it is. And then there are another 2, sorry. Okay, but I don't find, okay, one is this, 3 and 1, and another one in the same situation. This is C1. Another one that traverses some vertex, the 4 faces of some vertex consecutively is, no, this is C3, sorry, C2. And it does it for 2 open vertices, not just 1. This one, the 4 faces, and this one. So it is a different cycle from the previous one. And these are the 2 cycles traversing consecutively the 4 faces for some open vertex. Then there is 1 cycle connecting, traversing 3 faces. And this happens for 4 vertices marked with a yellow dot. This is one, another one. Okay, and for the other two open vertices, there are two faces and then two faces. Then the last two cycles, C4. The other two cycles never traverse more than two faces consecutively. And this one, for two closed vertices, the ones with three faces, traverse the three faces in three different moments, one and the opposite one, while the others are traversed three faces together. And indeed it is a zigzag along the equator of the voxel. And the last one, C5, for no closed vertex, it traverses the three faces separately. Either they are together consecutively, or they are 2 plus 1. And so it is not equivalent to the other one. Okay. Return to the slides. Okay, I'm no more in screen. Okay. Okay. I skip the slides for the cycles because we have already seen. Before going to proposition 2, let's stop a bit to see how a cycle can traverse a phase. Either entering and leaving it from two opposite edges or from two edges that consecutive edges that share a closed vertex or an open vertex. This last situation with the closed vertex, the open vertex, sorry, does not happen in the last two cycles, C4 and C5. Okay, now proposition 2, for each tree-like object, there is an Hamiltonian cycle connecting the faces, and this cycle can be constructed by using just one cycle, Ci, modulo rotation and symmetry, on all the voxels composing the object. The proof of this proposition is by induction on the number of voxels, and of course on one voxel it is obvious. If the object has n plus 1 voxels, then we can always, okay, it is tree-like, so there is always a leaf voxel, and we can choose one and remove it. For example, this one, and we remove it. And the resulting object has just n voxels, so the proposition is true on it, and there is a Hamiltonian cycle using cycle Ci on all voxels. And we consider how this cycle traverses the common face to the removed voxel. It will traverse it in one of the three possible ways. And we choose on this missing voxel, well, the removed one, a variant, a rotated or symmetric variant of Ci that traverses this face in the same way. And we attach to the object the other voxel with that cycle. Okay, this is the cycle and this is attached. And in this way, we have a cycle on the entire object. So the proposition is demonstrated. Okay, now the same inductive proof can be converted into an algorithm to generate a Hamiltonian cycle. Just we give the object and the index of the cycle to be used. And we start from one voxel with the cycle on it, and then we iteratively attach voxels with the corresponding cycles. And okay, this is rather theoretically, but one can say, well, what is the potential impact of these results? One immediate possibility is the generation of triangle strips for visualizing an object on the surface of an object in the FCC grid. And this is easy because we just consider how each face is traversed by the cycle. We triangulate it in one of the possible ways. in this case, we have two possibilities. In the other cases, we have just one. And this gives immediately a generalized triangle strip covering all the object surface. If we use the cycle C4 or C5, we have never this situation, so we can always triangulate with the better aspect ratio of the triangles. Okay, next. And for example, we have this triangulation on this, the aspect ratio is better on the yellow faces. But other possibilities that we have not explored, but they may be worth to investigate them. Okay, for mesh compression and transmission, these are two pictures from old works that consider compression based on paths of cycles of phases, and one may consider Hamiltonian cycles. Can they be convenient in these situations? Maybe. And another possibility is quite curious. There are some works that are about cutting a surface and unfolding it on a plane. And this has application for constructing an object from some material which can be folded, and one may investigate if Hamiltonian cycles can be help also in this situation. And there are maybe potentially other possibilities of use. Okay, and this is my last slide. Thank you for your attention, and I am ready for questions.
Thank you very much, Paola. Thank you for a fascinating topic. So I look at the, we still have participants, very good. Don't hesitate to, don't be shy, just ask questions into the chat. And in fact, I will start by one. You mentioned that this can be used for stripping, right? For decomposing a surface into a strip and so on. So do you think this can also be used for computing like space filling curves on surfaces, but with like probably good properties also? You know, there are also quality criterion or criteria for space filling curves. So do you think
maybe it is probably, it should be investigated, but probably yes. For example, if I remember, okay, previous. If I remember correctly, the content of this article, for example, they used some idea of space filling curve for covering the object. And probably one could compare Hamiltonian cycles with the other space filling curves to see what is better, if there are good, especially good properties in Hamiltonian cycles. So with respect to, I've not investigated, but I suppose that one it would be interesting too.
And in fact, there is a relating question in the chat, which says that yesterday, Ergun Ackelman and group talked about interlocking space-filling structures. Could that be another application of this approach?
Yes, I think so. I cannot, in this moment, I cannot imagine how, but I think that it could be a possibility.
So I have, in fact, another question relating to, you mentioned that this is also relevant for meshing with some probably good properties, right? For the shape of the elements and so on. And do you think this can also be combined with like continuous optimization, in which you could interleave between this like discrete optimization and then iterated with continuous optimization, such as vertex relocation and so on?
Do you mean that we also kind of optimization that in which we change the shape, the location of vertices?
Yeah, where we can do also combine with the continuous optimization, such as vertex relocation.
This is a FCC grid, so the vertices must be in,
right.
some specific positions, but maybe we could start from an object in a specific grid and then optimize the shape according to some cost function. Maybe we could use in some way also the Hamiltonian paths on it. I don't, maybe, probably.
Thank you. So there is another question by Silvia Biasotti in the chat. Is the existence of 5 Hamiltonian cycles an element of ambiguity?
Ambiguity, it
Maybe
depends
Silvia, you can precise
on on what you want to do with the Hamiltonian cycles. In some way, there are 5 with different properties. So if you have a specific application in which some properties are, for example, I just previous. Okay. If you look, I don't know if I have to go only one by one. Okay. Previous, okay. If you look, the idea of having 5 could be also useful. So you can choose, for example, you don't like this way for traversing the faces, you will choose C4 or C5 that have not this one. Do you want another one, a cycle which is I don't know, symmetric with respect to the center of the voxel, and you have one. A cycle that is symmetric with respect to an axis of the voxel. For example, if I return to the 3D visualizer, okay. For example, this cycle here, this one is symmetric with respect to an axis passing to the two red points, and it can be a property that you can choose. Other cycles are symmetric with respect to the center of the object. In some way, if you have 5, you can choose one with the specific properties that you may need.
Thank you very much, Paola. And in fact, thank you so much. And that concludes this talk. And in fact, that concludes the whole session of these 3 papers from the Shape Modeling International 2020 conference. So thank you so much for all the speakers. Thank you very much for all participants. I see we still have 15 participants. I would like to thank you all very much. You can continue the discussion on Discord, including offline and later. You can ask questions with more technical questions. You can probably also access the slides there. I think they provided links to the slide. Thank you very much, everyone, and enjoy the rest of the conference. Bye, everyone.
Bye-bye.
Bye-bye, Paola.